So today's lesson is about actually defining and measuring the rate of reaction. So yesterday we talked about collision theory and what has to happen in order for molecules to react. Now we're going to talk about how we actually measure that. Okay, so what we're going to do to define rate is the change in concentration, meaning like molarity or moles per cubic decimeter per unit time. So you'll see it written like this, moles per cubic decimeter per second. Now this could be minutes or hours, but it's usually seconds. Okay, and you could get a graph like this. Okay, so this is concentration versus time. Okay, so first off, is this graph a graph of a reactant or a product? How do you know? Well, hopefully you see that the concentration is decreasing with time, so if it's being used up over time, that means it must be a reactant. A product would have an opposite curve and increase and then kind of level off. So it levels off here because the reaction is nearing completion. Okay, so why does the rate decrease with time? In other words, why is this slope so steep up here and decreases down here? Well, it has to deal with concentration. There's a higher concentration here, so there's a greater frequency of collisions. As we decrease the concentration, we decrease the frequency of collisions, and so the rate decreases. Okay, we could also look at this graphically. So this is one of the ways we can analyze or determine rate. You are given a graph and say, well, what's the average rate of reaction from time equals 20 to time equals 40? So from 20 to 40 seconds. Well, guys, this is pretty standard algebra 1. We're going to find our 2 points and put the coordinates to them. We're not going to count squares because this is not like a 1-to-1 ratio. That is never the way to go. And we're going to do the change in concentration, so our change in y, over the change in time, which is our change in x. Okay. So I'll find my slope. And yes, that looked funny, but anyways. And that comes out to be 0.03 molarity per second. Remember, molarity is the same as moles per cubic decimeter, so we could write it this way. Okay, by the way, if you write it this way, IB will accept it. However, you need to know that IB will write theirs this way, so you need to be able to translate. Okay, so that's the average rate, the rate over a period of time, but we could also find what we call instantaneous rate. So meaning the rate at that specific point. And here's how we're going to do it. We're going to draw what's called a tangent line. Hopefully you've learned this. I know you've learned this in your math classes, but you draw a line that's tangent to it so that it intersects at that one point. And yes, my PowerPoint drawing skills are meh. But it intersects at t equals 20. And then I'm going to find the slope of this line, and the slope of that line is equal to the slope of that curve at t equals 20. So here's my 2 coordinates that I found. So it's going to be change in concentration over change in time, change in y over change in x. And I get 0.0533 moles per cubic decimeter per second. So notice that this value is greater than our average from 20 to 40 because as we went from 20 to 40, it was slowed down. Our concentration was decreasing. Lower frequency of collisions. Okay. Oh, hey, some of my stuff popped up early. Oh, well. Okay, let's take a look at this graph. It says use this graph to write a balanced chemical equation. So I see I have NO2 and NO and O2. So those are my 3 species, but we've got to figure out what's a reactant, what's a product. Well, NO2 is the one that's decreasing, so it must be my reactant. And these 2 guys are my products. So I'm going to write that. And that's not balanced. So we've got to balance. Well, you have 2 ways of balancing it. You can balance it by looking at this graph, and we'll come back around to that. Or you can just balance it old school and go, oh, I don't have enough oxygens. Okay, now we're all good. Okay. Now, here's where I'm talking about that we could use the slopes to balance the equation. If we look at the slopes of these various species, look at NO2 and NO, they have the same slope, but just opposite in sign, so equal magnitude, opposite in sign. Well, look at where they are on the balanced equation. It's a 2-to-2 ratio. Notice that oxygen at any given point has a slope about half of that of these guys. Well, look at that. There's 1 oxygen for every 2 of the NO. So it matches the mole ratios, and you can actually do some like stoichiometry based on this. So let's try that. The decomposition of dinitrogen pentaoxide is described by the reaction below. 2 dinitrogen pentaoxides forming 4 nitrogen dioxides and an oxygen. So if the rate of appearance of oxygen is equal to 2.4 moles per minute, what's the rate of disappearance of 2.5 or of N2O5? I don't know what I'm saying. I need more coffee. All right, so we're going to start with what we know. We're producing 2.4 moles of oxygen per minute. Well, if I look at this balanced equation, there's 1 mole of oxygen for every 2 N2O5s. So I'm going to multiply out my mole ratio. My oxygens will cancel out, and I'll get 4.8 moles of N2O5 per minute that's disappearing, okay, or being consumed. Okay, so let's talk about experimental ways to measure rates, okay, because we can graph them, but what are we going to graph in order to measure that rate? Well, there's a few different things, and it depends on the reaction. So our first one is the change in volume of gas produced. So this is good for a reaction that has only one gaseous product. So we have like solids or aqueous solution reacting to form a mixture of products, but only one of them is a gas. And so we'd have our reaction mixture in some sort of sealed container and a gas syringe, or we can collect it through water displacement, a few different ways of doing it, but we'd measure like, oh, we've got at 3 seconds, we've got 10 milliliters of gas. At 5 seconds, we've got 15, and so on and so forth. Okay, so some potential problems. You have to think about the effects of temperature. If this is a really endothermic or exothermic reaction, you're going to see a little bit of a skew with your data because gases change volume at those different temperatures. Also, we need to make sure that if we're collecting it over water, the gas needs to have very low solubility. If it dissolves well in the water, then we would have a systematic error of a low volume over time. Okay. So this is really good for, say, like magnesium and hydrochloric acid producing hydrogen gas and magnesium chloride. Next one is change in mass. So this is also good for a reaction that's producing a gas. Now, it doesn't work so well if we're producing a low mass gas like hydrogen because it just doesn't change in mass much. But if you think of that classic baking soda and vinegar, so sodium bicarbonate and acetic acid, it reacts to produce water and sodium chloride, and then carbon dioxide gas. Well, that carbon dioxide gas has substantial enough mass that if you put that reaction container on a flask, or in a flask, and put it on a balance, you could measure and you could take the mass like every 5 seconds or whatever and measure the mass of gas that's being produced. Okay, if you have something that changes from really colored to not, or the reverse, you can measure the change in transmission of light. Okay, so what we're going to have is we have our light bulb, and it goes through a prism to spread it out into the different colors, okay, diffracts it, and all that light is passed through the sample. Well, only some of that sample actually, or some of the light passes through, and so then we measure what sort of light passes through it, and is this solution or the sample either becomes more saturated with color or less saturated in color. We can measure that absorbance of light versus time and measure the rate. Okay, if we're doing something that changes in concentration, we could use a titration like a burette. So this is nice if we have something that's easily titrated, but we can't do it continuously, so we have to like do the reaction, quench it, which means stop it. Do the reaction for a little bit longer, quench it, stop it, titrate. Do the reaction a little bit longer, quench, titrate, and so it can get really arduous and tedious. Okay, Now we could also measure using conductivity. Remember, only ionic substances conduct electricity when in solution, when aqueous. And so if we have something that is going from ionic to molecular products or insoluble products, then we can measure plot conductivity versus time. This isn't really a problem so much as just a hassle, but you do have to standardize against solutions of known ion concentrations. So you have to be very, very precise. And like I said, it can be a little bit of a pain. Okay, and then lastly, we can use clock reactions, reactions with an arbitrary endpoint. So this reaction right here produces sulfur, a sulfur precipitate, so it sits at the bottom of the beaker, and it obstructs that blue X that's on the paper underneath the beaker. And so you can time how long until it covers up the X, how long until we can't see the X anymore. Of course, the problem with that is that it's somewhat subjective. But some other ways that you could do this. So if you were to do magnesium and hydrochloric acid, you could measure the time until you stop seeing bubbles. So the question is, do you go like, yeah, sure, it's not bubbling anymore, or are you going, oh, is there one more bubble? Is there one more bubble? This sodium thiosulfate and hydrochloric acid, that's the sulfur reaction that was in that other one. And here's an iodine clock reaction. I'm just going to show you. This is some neat planning on the behalf of this group of chemists. All right, so there you go. All right, so here's an example. We've got calcium carbonate and hydrochloric acid forming calcium chloride, water, and carbon dioxide. And it says, what are 3 ways that the rate of this reaction could be determined? So you think, carbon dioxide. So I could measure the volume of carbon dioxide versus time. We also know that if it's an open container, this would be losing mass. So we could measure the mass of the reaction container versus time. We've got hydrochloric acid, so we could measure the pH of it. We could also just measure the concentration of the acid, so with a titration, but we'd have to have a way to stop it. Or this calcium chloride, if we had a way of titrating that, we could find the concentration of calcium chloride versus time. And it says, for each method, sketch a graph to show how the value of the chosen variable would change with time. So we're going to do that. So the first one, all of these are going to be with time on the x-axis. Oh, let's focus that. And the first one was volume of CO2. So we think about this. It's a product, so it's going to increase, and we'll have that. Notice that it starts at the origin at 0. Okay, well, what if we had the mass of reaction vessel? Okay, so we have our reaction mixture. It's producing carbon dioxide. The carbon dioxide is escaping, so it's going to decrease. Notice it won't go to 0. Okay, that's much better. All right, our next one was time versus pH. Okay, so I'm getting rid of the acid. What should happen to pH? Well, you got to realize acids have a low pH, and so as we get rid of the acid, our pH will come up, but we're not going to start at 0. We'll just start low and do that. Okay. What if we had the concentration of the HCl, though? That would have a downward curve. And if we had our concentration of calcium chloride, it would have an upward curve. So there you go. Okay, your mastery checks are actually going to be printed tomorrow, but I want you to see the questions now so you can be prepared to answer them. Graphing is an important method in the study of rates of chemical reactions. Sketch a graph to show how the reactant concentration changes with time in a typical chemical reaction taking place in solution. Show how the rate of the reaction at a particular time can be determined. So at a particular time, not over multiple times. All right, here's your second one that'll be on your mastery checks. A solution of hydrogen peroxide is added to a solution of sodium iodide and acidified with hydrochloric acid. The yellow color of the iodine can be used to determine the rate of the reaction. The experiment is repeated with some changes to the reaction conditions. For each of the changes that follow, predict, stating a reason, its effect on the rate of reaction. So A, the concentration of hydrogen peroxide is increased at constant temperature. B, the solution of sodium iodide is prepared from a fine powder instead of a large crystal. C, the temperature of the solution is increased. So be able to predict and state a reason for those 3 effects on the rate of reaction. And here's your third one. Magnesium reacts with sulfuric acid. The graph shows the results of an experiment using excess magnesium ribbon and dilute sulfuric acid. Outline why the rate of reaction decreases with time, and sketch on the same graph the expected results if the experiment were repeated using powdered magnesium, keeping its mass and all other variables unchanged.